weird time for me to be giving a talk in a session about academic perspectives on cryptography, because I've left academia for the most part, and I'm now working for a US stock exchange where I build models to protect investors from predatory high-frequency trading. So happy to talk about that offline if anybody's interested. But I've been doing this kind of experiment lately in terms of cryptography research that can be done in your head while waiting for database queries about stocks on the market. And it's a little bit like we sometimes think about cryptography that can be done on lightweight devices, like what can you do if you have only a small amount of memory or only a small amount of computational power. So it's really forced me to simplify a lot of things, kind of what research can you do if you could only hold it in your mind while you're trying to do something else. And I've chosen a bit of a strange topic for it, which is program obfuscation. Because one of the things about the research of program obfuscation is we've managed to obfuscate the research a lot more than we've managed to obfuscate the programs. So simplification in this space has been a major goal of mine. And so what I'm going to show you today is an outgrowth of that, which is a pretty simple little scheme that obfuscates a very narrow kind of program, which is a small piece of what the grand vision for this research ultimately is, which is to take a piece of code and sort of obfuscate it as a black box so that even if somebody is sort of watching all the intermediary effects of the computation and reading all the variables along the way, that you can sort of hide from them anything that's not just learnable from the inputs and outputs. So the goal is to get to a picture like this, where you can give somebody code, they can use it, they can send in inputs, and they can get out outputs, but they can't otherwise reverse engineer or learn anything about what's going on inside the code. So it kind of seems to me like a fundamental piece of this larger vision a lot of people are talking about with AI, which getting programs to do human-like behavior. Essentially, this is getting a program to lie by omission. So not tell you anything that it doesn't need to tell you in order to do its job. And it was shown by Brock et al. In 2001 that this grand vision formulated in exactly this way, that you couldn't learn literally anything beyond what you could learn from the input-output behavior, is impossible to do for all programs. And so what has sort of come out of that is two different branches of research. One is sort of building up what kind of programs can we do this for. We know we can't do it for all programs, but we can do it still for many interesting kinds of programs. And the other kind is to use a notion called I/O, which is indistinguishability obfuscation, which is a bit weaker than the fully black box picture, but it turned out to be surprisingly useful. So we found that if you assume I/O plus one-way functions, this becomes a kind of hub of cryptography that you can build a lot of other things from. So you can build functional encryption, multi-party key exchange, zero-knowledge proofs, signatures, pretty much almost everything we know how to do in cryptography and more. But what's difficult about this picture is it's extremely complex. So it relies on a lot of building blocks that themselves are very complex, and that we don't really have great instantiations of yet. In particular, this building block called multilinear maps, which is a bit of a speculative new mathematics based on lattices that may or may not hold up to cryptanalysis sort of over the long term. So trying to think about what can we carve out of this picture that's more simple. So we started with the simplest and most practical obfuscation schemes, which don't do all functions, but do very simple functions, and we've been trying to build up from there. And so the most basic example that you can start with is something called a point function. And so you imagine your program is very simple like this. It takes an input x, it has some binary representation of that, it does an equality check against some particular value, and if so, if it's equal to that, it outputs 1, and otherwise it outputs 0. So this is just a function with support on one point if the point happens to match that value. Now, obviously, if you look at the code sort of written this way, if you get this view of the code, you can see what that value that we're checking against is. But you can imagine if you had this as a black box, and you're just throwing in x's, and you didn't know what that value that was being tested was, you have a pretty low probability of guessing exactly that string, right? So it'd be hard for you to learn that secret value if you didn't, if you were just randomly guessing and you had this as a black box. And so a really basic way to sort of try to get this program closer to that black box behavior is to use something we're pretty familiar with in cryptography, which is a hash function. So if we use a cryptographic hash function that's very hard to invert, then if we simply hash the value and test against the hash value, then it should be hard for somebody to look at this code and see only the image of the hash and reverse engineer what the original point was. So you're not, in some sense, hiding everything about the code. You're not hiding the structure that it's an equality check, but you're hiding probably what the important piece is, which is what is the secret point that you're checking against. We're particularly interested in this kind of pattern matching functionality because there's some applications of obfuscation where this would start to get interesting a little bit beyond this simple version. For instance, if you know some kind of malware attack and you're building a software patch and you want to check if inputs are malicious in some certain structured way, but you want to put that patch out and not let it show people how to exploit unpatched machines, so you want to hide what the pattern of malicious input that you're checking, which is not too far away from this kind of point function. And you don't really have to hide the fact that you're checking a pattern as much as you want to hide the fact of what the exact pattern is that you're matching. So this is a very clean and very practical way to hide an equality test. But the entire purpose of hash functions is that that's exactly all that they do, right? If the hash had any more structure, it sort of wouldn't be a good hash function. So we really can't push this idea very naturally beyond this if we write it in this particular way. But there's a few other ways that we can hide an equality test, and some of them have the potential to go a bit further on what kind of functions they can handle. And so this is one that's going to be based on SubsetSum. So you could imagine sort of lining up all the bits of your input here against these sort of blocks, and you're going to give somebody two things for each possible input, and you're going to choose some set of numbers S1 through Sn that are random in some big field mod p up to the fact that they sum to 0. So the only structure is that they sum to 0, and you're going to sprinkle them across where you want the pattern to match. So if we're trying to test 0, 0, 1, and so on, we sort of put these numbers that add up to 0 in the slots that correspond to the bits of what we're trying to test. And then in the other places, we put random numbers. And now if I just give you these two n numbers, it can be very hard to figure out where is the exact sum that sums to 0. So if you had to test all of them, it would be 2 to the n, which if n is something like 100 or something like 500, then that's not going to be practical. So this is an assumption in cryptography known as the SubsetSum assumption, which is that under certain settings of the parameters, if we sort of sprinkle this structure of one hidden sum that sums to 0, it should be hard for you to find it, which is exactly saying here, it should be hard for you to find the point that we're equality testing. But if I give you all 2n of these numbers and you want to evaluate this function, then all you do is you sort of line your input up along the bottom here, and you take the numbers that correspond to your input values. So you take the 0 piece here, and the 0 piece there, and the 0 piece there, and you sum them up. And if you get 0, then you output 1, and if you don't get 0, you output 0. So we can give you this as a proxy for code that computes this function. And then you can actually compute this function, but it should be hard for you to guess that point. So at this point, we're very excited. We've got exactly back to where we were at the hash function, which in and of itself doesn't seem that interesting. But what we can do with this is we can embed a little bit more sophisticated algebraic structures instead of just sums in order to get to a bit fancier functions. So what are we trying to get to? So the next natural thing that we might try, something we call pattern matching with wildcards. So you could imagine that there's some bits of the input that you don't care about. So maybe the bad inputs that you're trying to filter out have certain bits in certain places, but in those other places you don't care what they are. You want to allow them to be either 0 or 1. So we'll call these wildcard slots. So you're going to specify your pattern only fixing some bits and leaving the rest sort of wildcard, and you want to output 1 if and only if you match in all of those non-wildcard bits. Otherwise, output 0. And notice here that you can't just use a hash function, because now you would get a list of all the possible hashes. So if your number of wildcards starts to be pretty big, that list is going to be exponentially long, and it's not going to be practical for you to check all those hash values. So you need to do something a little bit more structured than that. So if we think about this with a sum, one natural thing we might do is just take one of these wildcard positions and put the same value there. So if we don't care about bit 3, we can just put the secret value as 3 in both places, and now whichever one you use, it doesn't matter, the sum is going to be the same. And what's bad about this, of course, is that now I know exactly where my wildcards are. And if I didn't care about hiding where my wildcards are, then I could just tell you where the wildcards are and treat the rest of it as a hidden point function, and we can go back to what we were doing before. So one thing we'd like to take advantage of is the ambiguity and where these wildcards might be, and we'd like to hide from you those positions. So this kind of basic thing is going to preserve the function, but it's going to reveal too much. So because you can see these equalities, so you know exactly where the wildcards are. So let's try something slightly different. So let's instead choose a random degree n minus 1 polynomial. So we're going to use polynomial interpolation. So we're going to choose a random polynomial f, such that f is 0 at 0. And instead of putting these things that sum to 0, we're going to put the values of the polynomial evaluated at known points. Okay, so we'll put f of 1 over here. If this were a wildcard spot, we would put f of 2. So at every place that's allowed to be part of an input that matches, we put the value of the polynomial. At every place it's not supposed to match, so you see that in this first bit, we're declaring that it should be 0 to match the pattern. So here, when it's not, when it doesn't match the pattern, we're just going to put something random. And now what we have is a bunch of values, some of which are random, and some of which respect a polynomial structure. But if you don't know the polynomial now, these two values of the polynomial at different points, at least in isolation, look random. And they look the same as these other slots where you just have one polynomial value and one random value. And so you can start to play with this, and what happens though is as you get too many wildcards, you start to get in the range of Reed-Solomon decoding, which means you can do noisy polynomial interpolation, and you can actually figure out what the polynomial is, and therefore figure out which ones of these values are structured and which ones of these values are random. So as you get too many wildcards, you reach an overwhelming majority of correct values of the function, and you're able to reconstruct it. So we want to avoid that. What's interesting about this, though, from a sort of cryptography perspective, is that evaluating the function, so doing what you're supposed to do with this pseudo-encrypted code, is a linear function. So polynomial interpolation, when you know the points, you just take a linear combination of the values of the function. Whereas Reed-Solomon decoding and list decoding is a high-degree function. It's a nonlinear function. So we have the seeds of what we need to do cryptography. We have that the allowed behavior is a simple computation, it's linear. And the behavior that we want to stop people from decoding in a nonlinear fashion, is a higher degree computation. So it's a more difficult computation. So the gap between those is not an exponential time gap that we usually want for cryptography, but is nonetheless a gap. And so it leads us naturally to this question: how do we take that gap of linear function versus nonlinear function and amplify it into a gap that's big enough to be suitable for cryptography? And so we have this kind of landscape where we have a linear computation is what you're supposed to do with the points. We have a nonlinear computation, which is what the attack would be. And we want to separate these two things. Well, this is exactly a description of something called the generic group. Okay, so if you're familiar with discrete log-based cryptography systems, we often analyze them in this ideal world called the generic group, which essentially draws exactly this line, that in the exponent of a generic group, linear computation is allowed, nonlinear computation is not allowed. So what this means is that if we have some group generator G, we have some exponent A, taking G and raising it to the 8th power is going to be easy. Taking G to the A and G to the B and multiplying in the group, which means adding in the exponent, is also going to be easy. But finding the discrete log is something we're gonna assume is hard in these kind of groups. And doing any higher degree functions in the exponent, so doing something like a multiplication in the exponent, would be a quadratic function, we're going to also assume is hard. So we have candidate constructions for these kind of groups in finite fields and in elliptic curves, where you sort of believe this picture that these things are easy and these things are hard. And in fact, we have good reason to suspect that essentially everything nonlinear in the exponent is hard. So doing any kind of polynomials that are nonlinear in the exponent and these kind of settings is computationally hard. So if we have that, we can change our code a little bit. And so just to give you sort of the base case where we're doing an equality function, if you imagine taking your value and thinking of this binary representation as representing something in a finite field, so you can use it as an exponent, then instead of checking the equality directly, you check the equality in the exponent. And if the discrete log problem is hard, that means looking at g to the s is not going to tell you what s is. That's exactly the definition of the discrete log problem. So we can use these kind of groups to hide this equality test, but even more than that, we can use these kind of groups to hide this polynomial problem. So if we put these values in the exponent of such a group, then what we have is a polynomial interpolation that is a linear function, so that's easy in the group, or at least computationally doable, whereas the decoding that people would do to sort of define this hidden polynomial structure, if they didn't already know kind of where it was, would be a nonlinear function, and so the group computation would stop that. So this gives you an obfuscation of this kind of pattern matching with wildcards that can withstand a pretty decent density of wildcards. So it's a constant fraction of all the points can be wildcards, which is actually, this was also done previously with lattices. And so there was a previous scheme that contained this based on the learning with errors assumption. And so getting back to the theme of simplicity here, one thing that we're working on next is, but what is the simplest analog in lattices of this basic group structure? So group structures hide things by putting them in the exponent, which is what stops nonlinear computation. And lattice structures hide things by adding noise, which is also what stops nonlinear computation. So you can actually take essentially the same framework and write it down in a lattice structure with noise, and you get something that's actually different than what the previous known lattice scheme was. So something that's kind of interesting about this toy problem is that it starts to give you a little bit of insight into the fundamental bridges between group-based cryptography and lattice-based cryptography. And so we suspect that a simpler version of our scheme in lattices might essentially be showing, at least in this basic case, a sort of fundamental connection or translator between generic groups and lattice structures. And if we could bootstrap this to higher degrees of multilinearity, we'd start to chip away at this bigger problem of obfuscating all functions, where we know we need to hide higher degree functions and separate, let's say, like degree 2 computations from degree 3 instead of degree 1 from degree 2, which remains a sort of open problem for doing that in more standard lattice-based structures. Okay. I'll take questions if we have time.
So let's keep questions at the end.
Okay.
Okay. Thank you very much.